made another connection yesterday between gravity and electricity. We said yesterday that when we lift up an object through a gravitational field, we do work on that object. Here's an eraser. Right now, its gravitational potential energy relative to that desk is 0. When I lift it up, it gains potential energy. Let's say it had 0, and now when I lift it to a certain height, it has a gravitational potential energy of 20 joules. How much work did I have to do on this eraser to lift it from a potential of 0 to a potential energy of 20 joules? 20 joules. So the work done is equal to the change in gravitational potential energy. Well, electric potential energy works no differently. If I have an electric charge and I move it through an electric field, it also has to have work done on it. The work that's done on that charge as it moves through the electric field is equal to the change in electric potential energy. So let's say now that this is not an eraser, let's say now it's an electric charge. I move it against an electric field. I have to do work. Let's say I do 15 joules of work on this electric charge as I move it through the field. What's the change in potential energy that it experiences? 15 joules. But it's not gravitational potential, it's electric potential energy change. The equation is the same because in any way you look at it, the work is equal to the change in potential energy. The last thing we ended off with yesterday was this little sentence down here, the definition of electric potential energy. This is what looks a little bit different than gravity, but it's not really. We said yesterday that we define gravitational potential energy in Physics 20 as the energy stored in an object due to its height above the Earth. That's a good definition for Physics 20 because every time we do a problem in Physics 20 involving gravitational potential energy, it also involves the Earth. But strictly speaking, that definition should have been a little bit more general. It should have said the energy stored in a system of two masses a certain distance apart. The energy stored in the system of this eraser and the Earth while they're 1 meter apart. Or the energy stored in a system of this laptop and the Earth while they're 3 meters apart. The energy stored in the system of two objects a certain distance apart. The reason that we usually dropped the Earth part of that definition is because the Earth was always there. The Earth was always the second object. Technically, we could talk about the gravitational potential energy stored in the system of two objects. Object number 1, the eraser. Object number 2, Jack. But we don't usually do that in the context of gravity, right? So it's okay to drop the second mass because it's always going to be the Earth. But when we're talking about electricity, that second charge isn't, first of all, nearly as large as the Earth usually. And secondly, it's going to change. We can go from this charge being the second charge to this charge being the second charge in the next problem, to this charge being the second charge in the next problem, to this charge being the second charge in the next problem. Because both charges are changing versus with gravity, it's only the one mass that's changing. We have to use the more general form of the electric potential energy definition. That is the energy stored in a system of two charges a certain distance apart. All right, easy, right? Let's do the easiest problem that you will ever see in Physics 30. It says, moving a small charge from one position in an electric field to another requires this much work. How much potential energy is going to be gained? This is really, really easy if you remember that work is equal to the change in potential energy. If you don't, then this is not an easy question. If you remember that work is equal to the change in potential energy, then we know that the potential energy change is simply going to be equal to 3.2 times 10 to the minus 19 joules. Does that make sense? If you remember this, then I think this is going to make sense. If you don't remember this, then this isn't going to make any sense whatsoever. I would like you to take a look at these two questions, and I'll give you literally 30 seconds to a minute to solve those. You don't even need to write them down if you don't want. They're going to be so quick. But I am going to cover up the answers because I wouldn't want to make it too easy for you. See what you can do with those over the next 30 seconds or so. Who's got the answer for question number 1? Here's the gain in potential energy. What's the work done? Same thing, right? 1.6 times 10 to the minus 19 joules. Okay, number 2 is a little bit tougher actually, but still not crazy hard. Number 2 says, here's what the potential energy was, and here's what the potential energy is. What's the work done? Matt, what is it? Yeah, it's 1.6 again. It's the difference between 8.0 and 6.4. So in both cases, the work done is equal to the change of potential energy, which is 1.6 times 10 to the minus 19. Good? Easy enough, right? All right. Now I want to talk about electric potential energy between two parallel plates. I'm going to give you an analogy to help you maybe, an analogy that we're going to carry through today to help you to maybe understand some of this stuff. We're going to say that electric potential energy is going to correspond to money. We're going to say that in this class, there's 25 people. I'm not going to count because I'm missing a couple of people today. We got around 25 people. Let's say it's exactly 25. I think it's actually more like 23, but we'll say it's exactly 25 because the math is easier. And let's say that we have a total amount of money in this class between us all of $100. Okay? We're going to say that the money in this class, $100, corresponds to the electric potential energy. Okay? It's the energy stored in the system of two charges a certain distance apart. The total amount is $100. Got it? Okay. We're going to say that change in money, that change in electric potential energy is equal to whatever you spend, or whatever we as a class spend. So let's say we go down to 7-Eleven with our $100, all 25 of us, and we spend a total of $25. How much potential energy did we have? 100. How much potential energy do we have now? 75. What's my potential energy difference? 25. What's the work done? 25. Does that make sense? The work done is equal to the amount of money that we as a group spent. Now, the work is equal to the change in potential energy, but as you know from physics 20, it's also equal to F times D, the force times the displacement. But it's important to note that this force is a component of the force that is parallel to the displacement. So, if I have an electric charge in an electric field that's pointing downwards, maybe that charge is a negatively charged particle. In an electric field that points downward, we know that that charge will experience a force. That force will be upwards, opposite to the direction of the field, because it's a negatively charged particle. If the force on it is upwards, and it moves upwards, in other words, the displacement is upwards, then the work done on this negative charge, therefore the change in potential energy, is simply equal to F times D, because F is parallel to the displacement. But let's say we introduce another charge. Let's extend this electric field down here. And let's introduce another charge. This time, the force is still going to be upwards because it's still opposite to the direction of the electric field. But this time, the movement of the particle, for whatever reason, is this way, to the right. How much work is done on this particle now as it moves to the right, but yet experiences a force upwards? It would be 0. It would be 0. Good. Why would it be 0, Matt? Because its displacement is not caused by the force. Its displacement is perpendicular to the direction of the force. You guys remember in physics 20, we sometimes tacked on a cos theta onto the end of that equation? Yeah, what would theta be in this case? The angle between F and D. Okay, what's the angle between F and D in this case? 90 degrees. What's cos 90? 0. What's F times D times 0? 0. So if you move a charge parallel to the field, then the work is equal to F times D, and it's also equal to delta E. If you move a charge perpendicular to the field, then the work done is 0, and the change in potential energy would be 0. Okay, let's use another analogy here. You're walking down a hill. Okay, you're walking down a hill. You experience a change in potential energy, right? There's work done. But then you decide, oh, there's somebody on the other side of the road that you want to chat with. So you walk across the road horizontally, not up the hill or down the hill. What's your change in potential energy as you walk parallel to the hill? 0. So the work done is 0. Well, if a charged particle moves perpendicular to the field, like you do when you walk across the street, but not up the hill or down the hill, the change of potential energy is 0 for you walking across the street, then the change of potential energy would be 0 for the charge moving perpendicular to the field as well. All right, let's go back to our analogy going to 7-Eleven for a second. We said potential energy was $100 in this class, right? When we went to 7-Eleven, we had 75 when we left 7-Eleven, so our potential energy difference was 25, or the work done was 25. The guys at 7-Eleven did $25 worth of work, therefore our change in energy was 25. Now I wanted to find another term. It's almost the same. Not electric potential energy, but electric potential. So just drop off the energy. Potential is the energy per unit charge. What does that mean in terms of our analogy? Well, if the potential energy of this class was 100 joules, then the potential would be 4. Where does that come from? 100 divided, go ahead. It's how much each one has, each person. If we consider each of us to be a coulomb of charge, then the amount of money per coulomb would be 4. That's potential. Potential energy is the total. Potential is the amount per person or per coulomb of charge. So we have $100. That's our potential energy. Our potential is 4. We go to 7-Eleven. Okay, we're going to go to 7-Eleven. We drop $25. Our potential energy was 100, now it's 75. Our potential energy difference is 25. Our potential was 4. What's our potential now? 3. What's our potential difference? 1. Remember we talked about potential difference over the last couple of days in the context of plates? Now you have a little bit better idea as to what potential difference is. It's the difference in energy per coulomb of charge. Potential will be given by the symbol V. That's a capital V, by the way, not a lowercase v. That would be speed. Capital V is equal to energy per charge, energy per coulomb. Units we could say are joules per coulomb or volts. As opposed to our potential difference, which is the change in energy per coulomb. It's 4 minus 3, right? If we're talking about our money again for a second, right? Our final potential was, sorry, actually 3 minus 4, right? When we left 7-Eleven, we each had $3. When we went in, we each had $4. Or you could look at it a little bit differently and say that the change in energy that we experienced as a class was 25, but there were 25 of us, so the change in potential, or the potential difference, was -1. So whether you subtract the final potential from the minus the initial potential, or you divide the change in potential energy by the charge, you get the same answer, -1 in this case. Potential energy, 100. Then it's 75. Potential energy difference, 25. Potential was 4. Then it becomes 3. The potential difference is -1. Usually we just call it 1, actually, even though it's a minus. Last question. The only other thing we're going to do today here. Page 565 says, moving a small charge of 1.6 times 10 to the minus 19 between two parallel plates increases the potential energy by that much. So we're going to say that variable is what? Is it E, delta E? Is it V, or is it delta V? Energy, change in energy, or potential difference? Delta E. It changes not the electric potential, but the electric potential energy. So we're going to say delta E is 3.2 times 10 to the minus 16 joules. We want to find... The electric potential difference is going to be delta V. Remember, potential difference, delta V. Electric potential energy difference, delta E. We want to find delta V here. It's going to be equal to, well, we can say VF minus VI, or we can say delta E over Q. Let's divide those two numbers together this time. We'll get the potential difference, either joules per coulomb, or we can say it's another unit for it, volts. Exactly the same thing. Get your homework over the weekend, besides your little assignment, of course, is going to be page 565, number 1 and 2.